In this module, I shall prove some of the very basic properties of the derivative. First, let's start with a very simple proposition. Suppose I subset of R is an interval f from I to R is a function and C is an element of I. Suppose f is differentiable at C. This just means, as you can guess, that the derivative at the point C exists. Then f is continuous at C. The proof is fairly easy. Let's consider what the second interpretation of the derivative as a good linear approximation allows us to prove this quickly. Let's see how it does that. We know that f of x is equal to f of c plus f prime of c into x minus c plus this error term of x minus c into x minus c. Okay, now take limit x going to c on the RHS. Okay, this will vanish and so will this, right? Hence limit x going to c of f of x is just equal to f of c. We are done. So we got the proof instantly once we used the interpretation of the derivative as giving a good linear approximation. Many other properties will also follow quite easily from this. Let's consider the various algebraic properties of the derivative. Algebraic properties of the derivative. This time f comma g are functions from I to R. Then suppose f prime of c comma g prime of c exists. Then f plus g prime of c is just f prime at c plus g prime at c. In fact, I can put a plus or minus also. This one I'm not even going to bother proving. This is so utterly easy. Second, fg prime at c is f g prime at c plus, sorry, I should mention which point f is taken at. It's f of c g prime at c plus f prime of c g of c. This is also called the Leibniz rule. Let's prove this. So, as is familiar, I will just rewrite f prime of c as f of c plus h minus f of c by h. Of course, I must write f prime of c equal to limit h going to 0. Now, one trivial remark, but still nevertheless has to be made, is that the point c could be one of the endpoints of I. I am not specifying whether I is an open interval or I is a closed interval. I am making no such distinction. I is just an interval, and it can happen that the point c is one of the endpoints of the interval. In which case, when I write limit h going to 0, it obviously means the corresponding right hand limit or left hand limit, as the case might be. as this is not such an important point, I will not be extra scrupulous and simply write limit h going to 0 with the understanding that the choices of h is to ensure that this c plus h is there in I. Okay, always the h is chosen so that the c plus h is in I. This is implicit. Okay, now I have just rewritten the usual definition of derivative in terms of the variable h. That this is equivalent to derivative is easy to see. Equivalent to derivative is very easy to see. The usual definition involving f of x minus f of c by x minus c as limit x going to c. This and this quotient will exactly be equal to that quotient in the limit. Okay, so now that we have rewritten like this, let's write what fg should be. So fg prime at c has got to be the limit of some quotients. So let me just write those quotients. It's got to be fg of c plus h minus fg of c divided by h. I want to analyze this quotient. Well, of course, we pull the standard trick that we are all familiar with. We write this as f of c plus h, g of c plus h. So that this is understood. G of c plus h minus f of c plus h, g of c plus f of c plus h, g of c minus f of c, g of c by h. The standard plus minus, add something, subtract something, that gives you the answer. Okay, now this will be equal to f of c plus h times g of c plus h minus g of c by h plus g of c into f of c plus h minus f of c by h. Taking limit h going to 0 immediately gives the result. Now we come to the next property, which is the quotient property. So number 3, if g of c is not 0, in addition to assuming that g prime of c exists, then 1 by g prime at the point c is just equal to minus 1 by g squared of c times g prime at c. Okay, no assumption on the derivative at the point c other than that it exists, but we need to assume that g of c is not 0. Okay, now note that this 1 by g is defined only in some neighborhood or some ball around c intersection I, this interval I. This 1 by g is not a globally defined function on the whole of I. It can happen that even though g of c is not 0, g could be 0 at some other point. Okay, so let's prove this. First 1 by g is indeed defined. I'll just abbreviate this as saying near the point c, because g of c is not 0 and g is continuous. At c. Because of the epsilon delta definition of continuity and the fact that g of c is not 0, we can find some small enough ball around c such that the value of g on that ball intersect I will also be not 0. This just follows from continuity and the epsilon delta definition. And 1 by g is indeed going to be well defined there. But we cannot say far away from this point C whether 1 by g is going to be well defined. Now, let's write down what the derivative of 1 by g is got to be by writing the quotient. So, we need to compute 1 by g of c plus h minus 1 by g of c by h. We have to compute the quotient of this. Well, that's rather easy. We just do LCM and this will give you g of c plus h times g of c, and in the numerator we will get g of c minus g of c plus h, and this h which was originally there will go here. Now when you take limit h going to 0, you clearly get g prime of c with a negative sign because there is the order has gotten mixed up now. Because of that you get g prime of c and the denominator just becomes g squared of c, which is what was required, which is what we needed. Okay. So the derivative of 1 by g is minus 1 by g squared times g prime of c. So exercise formulate and prove a quotient rule for f by g. Okay. Again, this is all familiar from high school. In fact, even the proofs are more or less the same, except now that all we have done is we have the background definition of limit rigorously done. In school, you did not have the background definition of limit rigorously done, but the proofs are exactly the same. The only difference is the certain properties of limits you took it for granted without really getting to the guts of the thing. We have already done that work. So essentially, what I'm doing is a repeat of what you have done in school. So I will be going a bit fast. Okay. Now we come to the famous chain rule. Theorem, chain rule. This often perplexes students because you would expect the derivative of g composed with f not to be just such a simple product. Now let's write down a precise statement. Let f from I to r and g from j to r be functions. Assume first that f of I is subset of j. This is strictly not needed. You can do a better, more ugly but more refined version of this. I'm not going to do that. You think about how to replace this hypothesis with a more refined one, but it will look ugly in the after I finish the proof. F is differentiable at the point C in I. 3. G is differentiable at the point f of c in j. Then g composed with f, the derivative at the point c is nothing but the derivative at the point f of c times f prime of c. Let's prove this. Proof. We will again use the linearization version of the definition of derivative. So we already know that f of c plus h is equal to f of c plus f prime at c times h. So no need to put a parenthesis, times h plus this error term of h into h. Let me call this E1 if you don't mind. Similarly, g of c plus k, not c, g of f of c, which I'll just call d. So let me just write that first. let D be f of c, then g of d plus k is equal to g of d plus g prime d times k plus e2 of k times k. Okay. Now what you do is set k to be equal to f of c plus h minus f of c. Fine. Now all this will make, so there are several underlying trivialities that as usual I am pushing under the carpet for you to fetch. The thing is, this f of c plus h minus f of c, this value k that you get, that should ensure that g of d plus k is defined. Okay, that should ensure that g of d plus k is defined, and indeed that will happen if h is really small, because then f of c will be very close to f of c plus h, or rather f of c plus h will be very close to f of c, and all these manipulations that I am about to do will make sense. So let's write down what this gives us. This gives us g of f of c plus h, because k is f of c plus h minus f of c and d is just f of c, we get g of f of c plus h is equal to g of f of c plus g prime of f of c times f of c plus h minus f of c plus e2 of f of c plus h minus f of c times f of c plus h minus f of c. Okay. Now what you do is you take g of f of c to the other side. So g of f of c plus h minus g of f of c is equal to g prime of f of c times f of c plus h minus f of c plus e2 of f of c plus h minus f of c multiplied by f of c plus h minus f of c. Okay, this is what you will get. Now dividing both sides by h, and taking h going to 0. Let's see what happens. So divide both sides by h. Divide both sides by h and take h going to 0. Okay, what you will end up with is g prime of f of c times f of c plus h minus f of c, this divided by h, plus e2 of f of c plus h minus f of c multiplied by f of c plus h minus f of c divided by h. Okay, I hope I haven't made any errors. I don't think so. Now as limit h goes to 0, this quantity just becomes f prime at the point c, right? And this quantity also becomes f prime at c. But this quantity which is there inside E2, this will approach 0 because f is going to be continuous at the point c, because f is differentiable at the point c. And we know that as the inside part of E2 goes to 0, E2 must also go to 0. In fact, E2 multiplied by h in fact E2 divided by h itself will go to 0 as h goes to 0. So even without that division by h, it has to go to 0. So this whole thing as h goes to 0 becomes g prime of f of c times f prime of c as required. So viewing derivatives in terms of linear approximations gives a more transparent proof of the chain rule, at least in my opinion. This is a course on real analysis, and you have just watched the module on the basic properties of the derivative.